Okay, this is Chapter 11, Organic Chemistry, Lesson 1. As I said in class, we're going to break organic chemistry into two smaller units. The first exam will cover characteristics of organic compounds, naming and writing organic compounds, and then the second exam will concentrate on the 7 organic reactions that you need to know. In this first lesson, we're going to differentiate between organic and inorganic compounds based on structure, name, and general characteristics. And we're also going to be able to differentiate between aliphatic, aromatic, saturated, and unsaturated compounds. Now, I know that sounds like a lot of big words, but really once you get into it and we start working with it, you'll see it's really not that difficult. So organic chemistry is the study of compounds that contain carbon and hydrogen. And one thing that's unique about carbon is because it has 4 valence electrons, which you know it's in group 14, and these 4 single bonds spread out evenly to create a tetrahedral. It's sometimes referred to as a regular tetrahedron. So we're talking about the same thing. The angles are 109.5 degrees, and this is really over here on the left is a great three-dimensional drawing of what it looks like. Now, on paper 2D, it really is drawn like this, but you'll know that it's fine for you to draw it like this. Okay, this is Regents Chem. You don't actually have to draw it so that it looks like it's 109.5. So this is also acceptable. Carbon atoms share electrons with other carbon atoms, okay, because if we're talking about carbon and hydrogen, then we're talking about covalent bonding, and we know that in covalent bonding electrons are shared. So carbon is sharing electrons with other atoms, and it can form covalent chains. So we're going to look at chains. We're going to look at straight chains and branched chains. We're going to look at rings, and then we're going to talk about networks. And actually, we've already talked about a network solid, okay, 2 network solids. We've talked about diamond, and we've also talked about graphite, which is really just carbons, but they do form networks. And these are also allotropes because they are the same element. 2 adjacent carbon atoms can share up to 3 pairs of electrons. And it's very important that you know that each pair is a dashed line. So over here, this dashed line right there, that represents 2 electrons. 1 coming from carbon and 1 coming from hydrogen. Hydrocarbons, organic molecules that contain only carbon and hydrogen. Thus the name, hydrocarbon. Okay? We have what's called saturated hydrocarbons, all single bonds between the carbons. So you have the maximum number of hydrogens attached the same way a saturated solution holds the maximum amount of solute. And you can see this if you look in table Q. Okay, there are examples of saturated and unsaturated hydrocarbons, which we're going to talk about, alkanes, alkenes, and alkynes. Now, you will not find the word saturated anywhere on your reference table, nor will you find the word unsaturated. So you have to memorize saturated hydrocarbons, all single bonds. So here you have an example of a saturated hydrocarbon. It's saturated because it has all single bonds, and it's a hydrocarbon because it contains only hydrogen and carbon. Now, I'm going to go ahead a little bit. If we were to go to name this, we would go to table P, and we would look and see the prefix for 3 carbons. So 3 carbons, right? 3 carbons has the prefix prop. You don't have to memorize that. Then if you go to table Q, you'll see that compounds that have all single bonds are called alkanes, and we take the ending of the name and we put it together with the prefix and we get propane. So this molecule right here is called propane. Unsaturated hydrocarbons have at least one multiple bond. Well, what do I mean by a multiple bond? A multiple bond refers to a double bond, which is like this, or triple bond. So if I refer to a multiple bond, I'm referring to a double or triple bond. So if something's unsaturated, it has at least one multiple bond. Here, this is an example of an unsaturated hydrocarbon with a double bond. Again, I count the number of C's, 1, 2, 3. All of these can be this doesn't look like a straight chain. However, I can get from one C to the next C without lifting my pen off the paper, and that becomes very important in naming. So again, my prefix is going to be prop. So if we go to table Q and we look for something that's got a double bond, we can see that it comes from the alkene family. So we're going to take our prefix and our suffix, and this would be propene. So you need to memorize unsaturated hydrocarbons have a multiple bond, so either a double or a triple bond. Here's an example of an unsaturated hydrocarbon with a triple bond. So 1, 2, 3, again, my prefix is going to be prop from table P. If I go to table Q, I see the example with a triple bond is called an alkyne, Y-N-E. So I'm going to take that suffix, and this actually would be called propyne. Okay, let's look at some properties of organic compounds. First of all, I mentioned already that they are covalent or molecular. Remember that these two words are synonymous. We learned that in the bonding unit, which means it's a metal and a nonmetal. Solubility. Most are insoluble in water. Why? Because organic compounds are generally nonpolar and water is polar. And you learned that like dissolves like. So polar only dissolves polar and ionic, and nonpolar only dissolves nonpolar. Conductivity. Most are non-conductors. Most are non-conductors in the solid, liquid, and aqueous states. The only thing that has some conductivity is an organic acid. Remember that an organic acid, and I mentioned this when we did the acids, bases, and salt unit, organic acids have the ending COOH, okay? But these are weak acids, so they only slightly dissociate. And we already learned this, but I just want to refresh your memory. By dissociate, what I mean is, let's take acetic acid. You're working with that in your titration lab right now, HC2H3O2, or it can be written as CH3COOH. So there's your clue that it's an organic compound. So when this dissociates, okay, what you have is HC2H3O2. And what we mean by dissociate, it splits into H plus and the acetate ion. And it minimally does this because it's a weak acid. This is only about a 5% dissociation as opposed to a strong acid, which would be 100%. So if it only 5% dissociates in water, what that means is that it's not very conductive. Okay, melting and boiling points. Because they're nonpolar, we know that they're going to have weak intermolecular forces. Weaker intermolecular forces means lower melting and boiling point. So this comes from the fact of it being nonpolar, or most of them being nonpolar. And reactivity rate. They react very slowly, okay? And the reason being is because most of them are fairly big molecules. And that means that they have a high number of bonds, and therefore there's more steps in the reaction to break them down or get them to react, and the reaction takes longer. So these are some really good characteristics that you should know. So we have two types of chemical formulas. We have a molecular formula, which shows the number of atoms of each element. So propane, C3H8, that tells me that this compound has 3 carbons and 8 hydrogens. That is a molecular formula. Then we have what's called a structural formula, which actually shows the arrangement of the number of atoms of each element. So if I were to draw out propane, I would simply just do 1, 2, 3, and then I've got 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Now, I will not draw every little H. You will just see me draw this. It is implied in organic chemistry that if you have a bond line, that at the end of this bond line, an H, and only an H would be attached. If something else were attached, an N or an O, then you would actually have to write that. But if you just have a bond line, it's assumed that what would be attached is an H. If you forget one of the bond lines, let's say I told you to draw propane, and you did that, your answer is completely wrong, no half credit. It must show all of the bond lines in order to get credit. Okay, and then you have the condensed formula, which is a combination of both structural and molecular. Now, I won't ask you, nor will the Regents ask you to actually write a condensed formula, but you have to be able to recognize a condensed formula and interpret it. Like you may have to take a condensed formula and draw something from it. So the easiest way to do that is to put a line in between where each of the C's are and break this up and then draw it. So I have CH3, so there's my C and there's my 3 H's. Now I have CH2, so I draw a CH2. And then my last C with 3 H's. So all I did was draw a line between the C's and I drew it step by step. Not so bad. Okay. Open-chained carbons are also referred to as aliphatic. So in this case, we're going to demonstrate the molecular formula. So molecular means I need to show the number of carbons and number of hydrogens. So let's count them up. So we have 1, 2, 3, 4, 5, 6. So I have C6. I have double those hydrogens. That's 12, 13, 14. So H14. Okay? Now, to write the condensed, I'm going to take this and I'm going to split it at each C. So, starting from left to right, I have CH3, I have CH2, I have another CH2, and yet another CH2, and I have another CH2, and then it ends in CH3. So this is the condensed. And I want to go back and check. 1, 2, 3, 4, 5, 6. I have 6 C's, so everything should be accounted for. Okay, the molecular formula here. I have 1, 2, 3, 4. So this is C4. I have double the H's, 8, 9, 10, H10. Let's do our condensed. So I have CH3 followed by CH2 followed by CH2 followed by CH3. I think you're getting the hang of this. And in the last one, we have 1, 2, 3, 4, 5, 6. So we have C6. Now we have H. I'm just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6, H12. Let's put this in the condensed. And draw my lines. So, starting from left to right, I have CH3, I have CH2, I have CH, followed by CH, followed by CH2, followed by CH3. So again, these are open-chained or aliphatic hydrocarbons. Next, I have a closed chain, which is called an aromatic, okay? And this can also be referred to as a ring. My molecular formula, 1, 2, 3, 4, 5, 6. So C6 and 2, 4, 6, 8, 10, 12, H12. So I want to point out something. See how this molecular formula is C6H12? And notice how this was also C6H12, but they look very different from one another. It's because they are, and they are completely two different compounds. Different name, different properties. What those are called, and I'm going to introduce this now, and you will learn about it later in the lesson, is isomers. They have the same molecular formula, but a different structural formula. And I'm introducing this now because I thought some of you might notice that and be like, that doesn't make sense. But it's true. So therefore they have a different name and different properties. When drawing organic compounds, you must always have 8 electrons around each atom. The exception is hydrogen, and it only wants 2, which we've discussed in regular bonding unit. Okay, so this table is going to be your friend. This is called the homologous series of hydrocarbons. Again, only contain hydrogen and carbon. We'll learn about other compounds later that include other things besides hydrogen and carbon. And these are all related to each other. Their members differ from one to another by 1 carbon unit. That's it. And there are always 4 bonds, 8 electrons around each carbon and hydrogen. Okay? Hydrogen gets 2 electrons, each carbon gets 4. If you have a diagram with, so if I drew something like this, this is not a valid compound. And the reason being is because this carbon right here has 5 bond lines coming off of it. 1, 2, 3, 4, 5. This is not allowed. Okay? I can draw something that looks like this, where in this case we have 1, 2, 3, 4, 1, 2, 3, 4. Actually, it would be drawn like this. I can draw something like this. So now each carbon has 4. This would be a correct diagram. This diagram is not allowed. Okay, so table P gives us organic prefixes, and table Q tells us whether it's an alkane, an alkene, or an alkyne. And we're going to use the general formula that you see here. CnH2n plus 2 for alkanes, where N equals the number of carbon atoms. CnH2n for alkenes, and CnH2n minus 2 for alkynes. Right away, you know that you have 3 carbons, so your prefix is going to be prop. But you don't know if it's propane, propene, or propyne by looking at the formula. So you have to see where it fits. So we go to the first formula, and we do C3, H, and then 2 times 3, because this is your number of carbons, plus 2. So 2 times 3 is 6, plus 2 is 8. So this is really C3H8, which is what we have. So we know that it's an alkane, and it's going to end in ANE. So this is propane. Okay, propine. Prop, we know it's going to be C3. Now we don't know how many H's it's supposed to have. So we go to the general formula for alkynes, which is CN H2N minus 2, and we plug in what we have. C3 H 2 times 3 minus 2. So 2 times 3 is 6, minus 2 is 4. So the formula would be C3H4. C4H8. Four carbons is bute. We get that from here. And we have to figure out what formula it fits. So let's go back to our first formula. If this is C4, H, 2 times 4 plus 2. 2 times 4 is 8, plus 2 is 10. It's not that one. Let's go to the next formula. C4, H, for your alkenes, 2 times 4. So C4H8, that's our formula. We know it has to be an ene, so this is going to be butene. Pent is 5 carbons, so this is going to be C5. And we know what ENE is because we just did butene. ENE is CnH2n. So double my carbons, so this is going to be H10. C6, 6 is hex. 10. Well, we know it's not the first formula because if I put 6 in here, 2 times 6 is 12 plus 2 is 14. That's not what I've got. I can look at the second formula, 2 times 6 is 12. That's not what I've got. In the last formula, 2n minus 2, 2 times 6 is 12, minus 2 is 10. So this is ine. This is going to be hexine. And the last one, hexane. Hex, we know is 6, so it's going to be C6. If it ends in ane, it's got to be an alkane, so it's going to be 2 times 6, which is 12, plus 2 is 14, H14. Okay, and that's our intro lesson. Have a great night.